Hello, I'm Jonatan Schumacher. I'm the Director of Advanced Computational Modeling at Thornton Tomasetti. Our Advanced Computational Modeling group was formed about 2 years ago in 2011, and our main purpose here in Thornton Tomasetti is we are a corporate entity. That means we don't only work with one office or with one of our 6 practice sectors, but we work with all of the different groups and with all of the different offices. And our main purpose here is parametric modeling. We do a lot of parametric modeling. We also focus a lot on interoperability and BIM workflow development. And as you will see from this presentation, we also have at least one leg always in the R&D side of things. And a lot of the services that we offer are supported by custom tool development. So we have quite a few programmers in our team. This presentation today will be about collaborative platforms. So how do we better collaborate within one office, and how do we also better collaborate in between different disciplines? I will start off this presentation by talking about one project that has been in our office for about 3 years now. This is the West 57th Street residential building by Bjarke Ingels Group in New York, West Side Highway and West 57th Street. For this project we are the structural engineer, and it's currently under construction. In the summer of 2010, as it happens so often, the building design changed quite frequently. As you can see, it changed from a 15-story building to a 20-story building to a 34-story building. Oftentimes there were only 2 weeks between one iteration and the next. And there are quite a few schemes that I don't actually show on this slide. So there were twisting towers in between these different schemes as well. And our challenge as engineers is to give back some useful feedback to the architect as they are in this conceptual design phase, where they frequently go through iterations. So for this project, we would typically be given one of these drawings, as we can see on the page here, that just says, okay, now it's 20 stories instead of 15, and now the top corner of the roof is at 280 feet instead of 250 feet, for example. And then we would have to try and turn around and turn this into a 3D model, analyze it to understand the total cost of structural components, and get back to the architect as quickly as possible. And in order to do this, we're using a software called ETABS. ETABS is a concrete analysis software that is very commonly used in the United States. ETABS at this point in 2010 did not have an API. They finally came out with one just now in 2013. And so the only way of automatically creating a model in ETABS was for it to read these text files, which describe all of the geometric information as well as material information of the project. And so for this project here, which we were modeling in Grasshopper, since we were really wanted to be able to change the roof height quickly and change the number of story elevations quickly, we developed a few plugins for Grasshopper that would help us let us assign different material properties and structural section properties to that geometry, and then it would create this text file in a format that ETABS can then read. So once the text file is created, we can simply save it as an ETABS file, and then we can go over to that program and we can open that file, and it will essentially have created the entire model for us. And so now at this point, our engineers could then go and start analyzing the geometry. So a few other tools that were developed somewhat in correlation to this project was, for example, a tributary area calculator, as you can see in the middle image here. So this tool for the whole building at once measures how much area of every slab belongs to every column. So cumulatively, you can see on the right-hand side in the Excel sheet quite nicely, it will just stack all of the area numbers on top of each other so that we can calculate the overall loads that go into a column and into the footings. And then in Excel we have some code that can size columns on a preliminary basis. the next project here is the Edmonton Arena that we're currently in the CD phase with 360 architecture. This is the Edmonton Arena in Edmonton, Canada, and it's we are the structure engineers for this project. In this case, we are not the facade engineers, but we are last summer we were assisting the local facade engineers with some of the more complex geometry resolution. So in this case, you can see we have these curved glass facades here, and the architect's intention is to have four-sided panels, but they don't want to be perfectly quadrangular panels or rectangular panels. Rather, they want to have some control over the angles of those panels. And in this case, we're using Kangaroo, a plugin, a form-finding plugin for Grasshopper, to essentially let us find the best panel shape and panel size that'll work on this particular surface, work in terms of out of planarity. So in this case, we're measuring the warpage of the panel, and we are color coding which of the panels don't work. And so you can in real time try out different panel configurations. So and it will then tell us whether the panels work or they don't work. So here, this is what it will look like over the whole facade, applied onto the whole facade. And this is a tool that we actually gave to the architects, and then they could work with their local facade consultants to make this project work. So ever since we started creating our own little structural analysis tools within Grasshopper directly, we thought it might be really interesting to also link that with a database that informs us about the amount of embodied carbon in a building. So typically every kilogram of steel of a certain grade has a certain percentage or a certain amount of embodied carbon. And we're using the database from the University of Bath, which has a pretty large breakdown of different material quantities. And so so we simply hook that up with our existing structure analysis programs that we have developed for Grasshopper. And so so here's a test case what this might look like. So here we have a building with 70,000 square meters of total floor area, and we can change things like column spacing. We can change the primary material from steel to concrete. We can change the overall building footprint, but the total square footage never changes. And it's really interesting to see how, depending on how these 70,000 square meters are laid out, the embodied carbon and the embodied energy per square meter of building area pretty much quadruples, I would say, in size, just depending on how we arrange the building to be. So we can change things like fly ash or slag or concrete strength, or we can add recycled steel content into the steel. So these are just kind of some tools that we're using that are basically informing the design already at the conceptual design phase. And now, kind of taking that one level further, this is the Morphosis designed this computer information science building at Cornell University. We were the structure engineers and the facade engineers on this project. We thought it would be very interesting to be able to calculate the energy consumption that this building might have as in terms of operation energy already during the conceptual design phase. And so we wanted to be able to parametrically control the louver geometry. We also wanted to be able to parametrically change the glazing type, try out different glazing configurations, and this would then, at every iteration, it would inform a daylight study, which would inform us about the lighting schedule. So it would tell us how many hours of the year can we use natural daylight as opposed to artificial daylight. It would also tell us a shading coefficient, so how much heat gain do we have falling into the facade, and all of this would then inform the Energy Plus model. So here is a demonstration of that in action, and this work was done with a student that we had in the spring of 2012 in our office. who was very interested in sustainability services and facade services, and trying to link those to using some of these advanced computational modeling tools. So here we can see with every iteration, as we change louver tilt or louver depth or material specs, we in series we run a radiation analysis, a daylight analysis, and then we can calculate the energy consumption of the building with a kind of default mechanical system in place. So the next project here is a R&D project that we did together with LMN architects up in Seattle. We were both very interested in kind of seeing how can we take what the architects do and what the engineers do, and how can we combine that as much as possible. So, you know, as I showed in the first example, the Bjarke Ingels example, typically the time spent between the architect creating one design option and the engineer getting back to them in the schematic design phase is something like 2 weeks for a fairly complex project. So by the time those 2 weeks are over, the design will have changed already. So this is basically our problem statement. What if the architect starts with a shell model or a massing model, then gives that to the engineer lays out all the columns and all the grids and calculates ceiling depths based on kind of beam depths, gives that back to the architect. Then based on the beam depths, for example, the architect will run some daylight concepts. Then they will give their results to the mechanical engineer. They will run an energy analysis, and by the time we have all this information kind of inform our final design, it's basically half a year later, and you know, this never really gets utilized. So we refer to this as linear analytics, where the architect comes up with a scheme, the engineer takes it over, analyzes it, and by the time they get back to the architect, the scheme has already changed. There's already a new scheme, so we don't really have an impact. So rather than doing that, how can we work really in parallel? How can we react to the architect's latest design as quickly as possible, and hence inform their current iteration as they are designing it? So together with LMN, we came up with this idea of setting up I want to say just a basic building geometry and material. Let's just say a BIM database in the cloud. In this case, we're using the Amazon Web Services, and we simply would have to agree on a common schema that both architects and engineers are able to write to and read from. And so as the architect then creates their different massing studies, every time they make a change, it will automatically write the latest geometry configuration to the database. Then on our server, our computer will automatically pick that up. It will run through the different analyses. In our case, in this video that I'm going to show now, it's running and calculating structural sizing, and then calculating embodied energy and embodied carbon values. And then it will give back the results to the architect. And this loop then takes maybe 2 minutes instead of 2 weeks. So here we can see on the left-hand side we have the architect's computer, and on the right-hand side we have the engineer's computer. And as the massing on the left changes, it automatically writes the latest geometry configuration to the server, to the cloud. Then the engineer's server picks it up, it calculates the sizes, and it gives back the results. So technically, it's definitely possible. It's probably more a question of, I guess, do we want to share all this information legally? But I think we should more and more. So kind of similar to that, we are also doing we also had this pretty intense project in our own firm, just kind of looking at the different services that we have as an engineer. So we have, you know, modeling, then we do the actual analysis, and then we do the documentation. This is pretty much always the workflow within our company, and even there's usually can be quite a disconnect, and so we've been kind of trying to come up with improved workflows for that. So this being a BIM conference, I thought I wanted to show this project. This is a recent airport project that we worked on. It's fairly large. It's about 1 kilometer in length, and when we were working on it last summer, we had only 2 months to go from DD to CD, and the challenge was to create a BIM model with all of these different elements being uniquely tagged. So the approach was the architect were working in Rhino, so the approach was to take the architect's model, then to use Grasshopper to attach unique IDs, element names, to the nodes and the lines, basically. Then to push that information into SAP 2000 by using the Geometry Gym plugin for Grasshopper. Then analyzing it and finding the structural shape sizes, and then taking the initial information of names as well as the shapes and putting all of that into Revit. And in this case, we were using IFC for that workflow. So again, Rhino from the architect, Grasshopper to generate the wireframe and BIM data, SAP 2000 to create to analyze actually the beam sizes. At this point, we would go into Tekla BIMsite, which is a free. In this case, we're using the clash detection part of BIMsite to see if our deflected structural model would actually not interfere with the architectural surface. And then once we were happy with the design, maybe once a week or so, we would push all of that into Revit structures for documentation. So very quickly it became apparent that this was a 3D analysis problem and not a 2D analysis problem. So one of our first tasks or challenges was to try and line out as many of the same truss types as possible. This video unfortunately is playing backwards, so you should be seeing those the red trusses are all of equal shape and equal size. So we want to use as many of them as possible to make the construction easier and therefore cheaper. Then, as you can see, we used the SSI tools to bring this into SAP. Then, once we had found the analysis model, we took the deflected geometry from SAP and brought it into Tekla BIMsite via IFC. And we also took that SAP model into Revit via IFC for documentation purposes. Now, IFC and Revit don't play too well yet, as we found. So, so as you can see, there are some openings here in Revit, which when we tested the same IFC model in Tekla, which is a different BIM modeler, it looked just fine. So the IFC data was clean. It was more the fact that Revit wasn't able to read it nicely. And also it took about, in comparison, it took about less than 3 minutes to open the model in Tekla, and it took about 6 hours to open it in Revit. So Revit clearly does something under the hood that didn't allow us to really accommodate those 60,000 different frames inside of Revit as 3D elements. So in the end, we decided, let's not use Revit for 3D documentation. Let's just use it to manage our drawings. And so, let me play this video again. And so we developed a plugin for Grasshopper that automatically would generate all of the different DWG files, all of the different drawing sections of the trusses, and export them to a folder. This is actually a tool that we're now giving away. If you download our TT toolbox for Grasshopper from Food for Rhino, you can get this tool. Then the next tool that we developed was for Revit was a tool that would import these DWG files. Then we developed one other tool that would place the imported views onto sheets automatically. So this is all work that normally would take, for a project of this scale, maybe 8 hours for each iteration. Now we can do that in, I don't know, half an hour or so. So here we have automatically set up all the sheets with the right title blocks and the right formats. And then the last tool that we developed was a placing the right view onto the right sheet, a tool for a sheet placement. So we can specify where on the sheet to locate the views, as you can see here. And we also developed a plugin for Revit to read native Word documents and Excel documents, so that it would actually recreate the kind of the Excel schedule with text that is native in Revit, so that you could manipulate the text after the fact. So with all of this, we were able to, in a fully automated fashion, document a large portion of the airport, as you can see here. So here we have all of the X, Y, and Z locations of all the different nodes. And then we also have the member sizes and member names documented here. And this was a lot quicker to do than dealing with 3D geometry in this case. So our typical workflow in our office is to generate geometry, then to analyze it, and then to document it. But very often, by the time we start the documentation, the geometry might have changed, or the analysis will be run again. So it's not really a linear process, but rather it's a very chaotic or chaotic process. And so we think rather than treating it like a linear fashion, we want to treat it as individual platforms that are all linked through one central platform in the middle. So so we started based on kind of what we had learned from the airport project and what we had learned from the previous research with LMN. We decided to start this TTX project. TTX is basically a platform-independent BIM database that will host all of the building information, and you can update it from all of the different software programs. So it's kind of like sync to central in Revit, but rather than just using Revit, we're using all the different programs, and we can always sync to a central database. The next video is going to demonstrate how this may look on a project similar to the airport project. So again, we're using Grasshopper to generate a parametrically controllable roof structure. And then we're using the SSI tools to push this information, this geometry into SAP, and then to calculate the structural sizes. And then once we have calculated that, we can then go back into Grasshopper and create a TTX project, and then we load that project into Revit. And now in Revit, this may now be the BIM department, for example, in our company, we're starting the documentation. So you can see here, where as part of the documentation, we're tagging the members with their names, which came out of SAP. And as the documentation proceeds, the geometry may change, or the structural analysis may be run again. So so typically at this point, we would have to kind of throw away a lot of the information that we already created in Revit or Tekla or any other platform. But now, since we have the ability to have a bidirectional link between all the different programs and the TTX database, we can simply update that project, and we will not lose any of the information. Rather, we're just updating now the model in Revit. So you can see all the tags are still linked, just the geometry has changed. And the same is true for Tekla. So if I forward this a bit further, you will see that we're also able to read this model into Tekla. So we can also, which I'm demonstrating in this video, we can also work in parallel in our office between Revit and Tekla really nicely. So again, the geometry may be started in Revit, then the model may be synced to the may be synced to the database, so that our Tekla modelers can then pick it up and modify it. And while the Tekla model is being modified, the Tekla and Revit will always continue to talk to one another. So now back in Revit, we can simply sync, and we can simply update the model, and it will create the latest beams from the Revit model. And now in Revit, we're going to make a change. We're going to change the story elevation, and then back in Tekla, once the database has been synced, we can also make that update. So so this is really allowing our company, our modelers in our different departments, to continue working on the same project in different software platforms. So we actually developed this as an in-house tool, but we're already starting to also use it for external services. The AC Martin architects for the Wilshire Grand Tower recently used this to bring across the slab geometry from their Rhino model into Revit. And we also set up a workflow on the template for them to use Chameleon for Grasshopper to bring across different facade elements. So we kind of provided them with a nice template file and some pieces of documentation to show how they in the future can use these plugins themselves. And I think this concludes my presentation. Thank you very much.